So let's consider, so that surface we just saw in the simulation, we'll pretend that this is, um, say air and water. So we transition between two surfaces. And let's say that there's some point P, all right, that we're going to send a light ray at. So we have a light ray come into this spot here, and it's going to refract. Let me make that more dramatic here, like this. And so we have a starting point at, say, point A, and some other point B that we want to pay attention to this transition of light, right? So if you just kind of think in this way here, we have some distance A that light is from the transition point, and we have some distance B that particle, if we're paying attention to a particle of light, a photon, and as it moves from where it was horizontally, there's some distance x, and if I were to try and pay attention to the entire horizontal displacement of light, if I wanted to call that, say, side C, well, then I have C minus x on that region there. Okay, so that's my C minus x spot, and then this would be the x distance. So this is just taking that same beam of refracted light that we saw in the simulation and making it static here, and basically setting it up so that we can take advantage of things using Pythagorean's theorem. Hopefully you're noticing the opportunity there. And it's, as usual, it helps us if we can take things and refer to them in terms of x and y lengths. That simplifies our math and gives us some advantages um, in that regard. All right, so we've set up this thing here, and we can start getting at what's going on here. So if we say that, a squared plus x squared would equal, we could, I guess, call that h squared. I already used c, so I have to use something else. And that means that length, h, is just going to be that. So it's a simple kind of math. And if I have, an angle alpha here, then the sine of that angle is just that ratio there, opposite over hypotenuse, or h in this case, and I went ahead and left it in terms of the other side. Then there is an angle beta down here that I could pay attention to, and the sine of that angle would be the thing that's opposite it, and this one's going to be the square root of b squared plus that c minus x side squared. So just doing the same math in that regard. So we've described parts of this model in trigonometric terms. So we've sort of left the physical aspect of it, and we're just trying to model it mathematically, and hopefully we obtain something that's useful. So that's just sort of link thing. Now it takes time for all this to happen. First zeroth law. Every change in position requires a change in time. And so there is a total time that we could pay attention to. So I'll come up here to the top. So total, of course it helps to spell it, right? Would be the time that it takes in air plus the time that it takes in water, or total up plus total down, or time up plus time down, however you want to pitch it. Well, I don't know the time in terms of seconds and whatnot, but I do know that the distance in air over the speed in air would be the same thing as time. All I'm doing is solving distance equals rate times time for time. And the distance in water divided by the speed in water. That'll give me my total time. And guess what I've done? I've already described the distance in air and the distance in water by those hypotenuse things, right? So continuing here, need a little bit of extra space. If I were to sort of put things in a different light here, using what we worked out before, I'm going to get rid of this stuff here so I have room to write. So all I'm doing now is taking the lengths of the hypotenuse for each part, and right now the only variable here is x. And so again, think of what's happening here. X is moving along here. X is the only thing that's changing. The length from A to P is a fixed length. The length from P to B is a fixed length. The speed in air and the speed in water are fixed amounts. Everything in this equation is a constant except x. It's the only variable. Now, many of you have had calculus, so that you know if you take the derivative and let it equal 0, that gives you some advantage. And even in algebra, you could find max and min of certain equations by letting things equal 0. So I'm going to bank on you knowing one or both of those things. All right, and so this lets us minimize the function. So whether you topped out in algebra or went to calculus, you've done that maneuver. I'm showing the calculus version since most folks in the course have had Calc 1. And so this is how things change with respect to x. And so we get a result from that. So I'm going to go to a clean screen here. So think back to moving from A to B, and instead of moving from air to water, think of moving from sand to water. You are at the beach, sitting in the sand at point A. At point B in the water, is your little brother or sister in danger of drowning? Okay. Do I have your attention? All right. So you have some choices. You could turn around and pretend you didn't notice. Okay. I don't recommend that. That would be cruel. Or you could get your rear and gear and go get your little brother or sister. And now you have choices about the path that you take. What's going to be the quickest path? A straight line between A and B or some other way? Um, you can probably move faster on the sand than you can in the water. So if you go on a straight line, you increase the amount of time that you spend in water, which is at a slower speed. So you would want to take a path that is perhaps almost perpendicular to the point that you want to go to in the water. Because what you want to do is minimize the time. That's what we just did, is minimize the time. And so you would choose a path that gets you to the water at a point where you spend the least amount of time in the water. And so this is what Fermat thought of in his principle of least time. And this is Snell's law arises from that kind of thinking. All right. And so somehow, does light have enough sense to think that way about what it's get all that math, but is because we were imposing our right triangle trig onto a physical reality. And one way to think of it is, what is the least time to get from A to B? And in the case of light transiting through a material, it's not a straight line distance. Normally, the shortest distance is the quickest time, but that's if you're in one medium. But if you transit through two mediums, not so much, because you will slow down in the other medium. And I'll show you what happens. So when we do this, we get a squared plus x squared. Well, I can write it that way, another algebra maneuver. So that's just putting it in a light so that when I do that derivative business, okay, we can follow those rules, bring the exponent down, etc., etc. So I'm going to kind of skip some of that, but let me write out for those of you who like the whole routine. When I do that derivative thing, that exponent comes down in front, but we'd got to do the chain rule business. And so a similar rigmarole over here. Sorry, that becomes a minus because you're subtracting 1 from it when you do that derivative maneuver. Be careful. So c minus x stays, but then that negative comes out from the variable x. And all that was equal to 0 because we were minimizing. Well, end result of all that is this. Get x over the airspeed times a squared plus x squared, and that's going to equal c minus x, the water speed, square root of that other side. And in one sense, it sort of, you could almost just reason straight to this point proportionally, because you had, if you remember, we had our transition Okay, and so here is that a squared plus x squared side. Here is the b squared plus c minus x squared side. This is x, and this is c minus x. So you almost expect proportionally that the relationship between these two things, okay, that you see right here, and the relationship between those two things that you see right here, you almost expect the proportionality in that regard, even though they're not similar triangles. And the reason you expect it is because of constant speed, which come in that form here. That's being a little loosey-goosey with the math, but just from a reasoning standpoint, it should be unsurprising that I obtained this proportion. But to do it legit, you'd have to do the calculus or some other minimizing function to get that. But this is the result of minimizing the time. All right? We get that proportion when we minimize the time. Now let me go back to the big picture that I had on the first screen before we move on from this spot. No, light doesn't have brains, but it has behavior that is like what I just described. It takes a path that minimizes the time. Okay, and why it's that way is another matter. But one thing I want you to notice is that this right here that was the sign of alpha in our last thing. And this right here, gotta keep getting my highlighters, this was the sign of beta. So what we can write is instead of all of that, we can say the sine of alpha over the speed of light and air will equal the sine of beta over the speed in water. So now we're not quite to Snell's law yet, but in that form, we've really simplified the geometry of this situation because measuring the sine of an angle is pretty easy. If you know the angle, you just jam that in the calculator, okay? And the speed, well, we know the speed of light in air and water. So we're onto something here. Those are fixed values. To remember all right. So we have two speeds that are fixed values. So speed in air, I'm going to use c even though it's not talking about the speed of light. Well, it is speed of light, but a particular value. And I'm going to create a new variable. And I have the speed in water, speed of light, relative to some feature about water. So this number, or this letter N, is an index, okay, for a physical property of the material. So where N1 and N2 are just some way to encode whatever is different about the medium's that light is moving through. All right. So let's think about this ratio of the speed of light c to something else. So I know that the speed through air and the speed through water are less than the speed of light. So if we're going to use this index, that's going to be our index of refraction, then I know in advance that those indices have to be 1 or bigger. And the reason they have to be 1 or bigger is because you can't exceed the value c, which is defined as the speed of light in empty space. It's at the maximum speed. So we know that these indexes are always going to be 1 or bigger. And we would define the index for empty space as 1, because it would just mean that your speed is the speed of light, the max speed of light. All right. These other indices are going to have to end up being bigger than 1, hence we put them in the denominator. All right. So that's the reason that we go at it. So if we go back to our proportion, we had sine of alpha, but now instead of speed in air, I do speed of light relative to this index, and sine of beta, I do speed of light relative to this other one. And of course, that drops out to sine alpha in air and sine beta index for water, right? Now, what we can do is just say, make it general and say I have this alpha angle and some index 1, and the sine of some other angle is going to be due to this index 2. So we generalize the medium, because whether it's air or water or glass or jello or whatever it is, it's going to be different. That material will have a property that causes light to behave in a different way than the other material. All right? And so this is Snell's law right here. And it describes how, if you think of that sine alpha, what was that describing? That was describing a path that light will take in a particular medium. And sine beta was the path that light takes in another medium. What the index did was define how the speed of light is diminished from its maximum value because of the material that it's in. So this proportion is a really simple proportion, but there's a lot going on in the mathematics there. A lot of physical description bundled up in that mathematics, and that's one of the uncanny things about mathematics is it yes. Well, the C's drop out. They're oh, they do switch. I'm glad you mentioned that. Let me sort of um, kind of got heard you a little off on the math there. So let's redo that just to be clear. Thank you for. If I go back, and I have C over N1, sine beta, C over N2. You're right. If I do this business, N1 over C, N2 over C, okay, well, then I just lose them. But what are we really trying to do here? What we need to do, I can take C out of both. I can just drop them. Sine alpha 1 over N1 would equal sine beta 1 over N2. And now what happens when you do this? You would have N1 sine alpha equals N2 sine beta, and then you have all of the versions, ways you could rearrange it. So we could have N1 to N2 equals sine beta to sine alpha, whatever floats our boat. So we could solve for indexes of refraction, we could solve for angles of incidence or refraction, etc., etc. All right, so Snell's law, that's kind of its classical form there. And I was almost right on the last screen. So that's where it comes from. And I would just